Perfect. So, hi everyone. My name is Sune. Wait, just give me a second. I'll have to. There's some echo, so I'll have to turn it down. I think that's good. So, hi everyone. My name is Sune. I'm one of the authors of a type-safe calculus for generating syntax-directed editors. And with me, I have some of the other authors who will also be available at the Q&A session later. So first off, I want to briefly introduce structure editors. So they were introduced in order to avoid syntax errors by letting us build the abstract syntax tree directly, while also putting constraints on how the tree can be edited. And this also offers the benefit of letting us skip the parsing process. In terms of early work, we have Bennetzen and Buus, who introduced the Cornell program synthesizer in 1981 for the PLI language. And in 1983, they presented the synthesizer generator, which can generate a structure for any programming language on the basis of a language definition. And Omar and others developed
Can I just interrupt?
The Hazel programming environment.
Can you hear me?
And with Hazel comes an editor calculus, which is a language for specifying edit operations. And here I want to note that Hazel itself is not a structure editor, but it introduces the notion of the syntactic holes, which inspired the foundation of our work.
Do we have a way of communicating?
And the foundation of our work is the type-safe structure editor calculus, which has been developed in a series of student projects at the University of Copenhagen and Aalborg University. And the calculus was first implemented by a group of students at the university.
Apparently.
And this talk presents a generalized version of that calculus and also an encoding into a typed lambda calculus. And this has two significant advantages. The first being that the encoding satisfies a general property of type safety, such that if well-typed, editor scripts will always produce syntactically well-formed programs. And also it becomes possible to devise an editor generator in a typed functional programming language. So the highlights of our work is the encoding.
Is it er det meningen din slide skal skifte?
Yeah.
Can you hear me?
Your slide is just the same.
Oh shoot. Thank you for pointing that out.
You can see we can see the new one now.
Should they be able to?
Okay. So it seems like when I go full screen, it doesn't follow. Okay, I'll keep it like this. Thank you. Yep. So okay. So I showed you some slides before. So this is from the Cornell program synthesizer. This is from Hazel. And here we have the type-safe structure editor calculus. So yeah. I think that this is almost where we got to, and then I mentioned that what our work is, and this is where I came to it. So the highlight of our work is that is the encoding and the proof of its soundness, and also an implementation in Elm of an editor generator based on the encoding. And our criteria for a good implementation are that we want to edit the abstract syntax of any program directly, and we want generic editing in the sense that we want to be able to edit the program of any given language given by its abstract syntax. We want to be able to handle context sensitive syntax. And we want multiple views of the code being edited, say, for example, a tree structure or a pre-printed view. And lastly, we want a non-challenging way of specifying the abstract syntax. And we also demonstrate the generality of our approach by showing how to handle 3 different language specifications. So we use the denotation by Harper to represent abstract syntax trees, where they are defined by a collection of sorts, a family of operators, and a family of variables. So let's say, for example, we have a small language with simple arithmetics. So we might have a set of sorts which only contains expressions, and then we have, let's say, a plus operator which has this arity, which should be read as the plus operator takes two arguments of sort expression and expression, and it returns an expression. But often a syntax will include binders. So following Harper, we can represent the syntax with binders by enriching the ASTs with bindings by assigning operators with a generalized arity, where they should be read as a vector of variables of sort x1 being bound to the argument of sort x1. So following up on the simple example from before, we can now extend it with a sort statement, and we can have a let operator which takes an argument of sort expression and statement, where the second argument binds a variable of sort expression within its scope. And now I want to present an editor calculus for an arbitrary abstract syntax. So assuming that we have an abstract syntax given by a set of sorts and a family of operators and a family of variables, then for every sort, we want to add a whole operator, which allows us to insert syntactic holes representing either empty or missing subtrees. And we add a cursor operator, which tells us where the editing currently takes place in the syntax tree. And our generalized editor calculus is defined by these formation rules. So first of all, we have the edit actions, where we have the prefixing, where the prefix pi can either be the child n operator, which moves the cursor down a level to the nth child, and we can move the cursor up to the parent, or we can insert an operator. And then we have conditionals, where if the condition is satisfied, we execute E1, and if not, we execute E2. And these conditions can either be negation, conjunction, disjunction. And we also have a model logic, which can tell us whether the cursor is currently at an operator, encapsulating some given operator. If some operator exists in some subtree, or if the operator exists in all subtrees. And we also have, unlike the Hazel editor calculus, we also allow repetition-based editor scripts using recursion. And also the conditions allow us to make edit actions conditional on the shape of the abstract text tree. So having the editor calculus, let's dive into the definition of the trees that we want to edit. So we first define trees without cursors, and these are crucial for defining cursor contexts and well-formed trees, which I will come to in a second. But essentially, the sorts here are made up by the sorts given by the abstract syntax, and the operators are made up of all of the operators from the given abstract syntax, excluding the cursor operator, of course. And then we have a cursor context, which holds information about the current tree surrounding the subtree where editing takes place. We represent the cursor context with an additional sort C, and the subtree that contains the cursor is represented with a context hole operator. And for well-formed trees are trees with only a single cursor, and and the cursor itself is essentially just one more operator, where which is added here in step 2 to represent the cursor currently encapsulating the root of a node, or either any of the immediate children of an operator. The semantics of the editor calculus are defined as small step semantics. I will not be presenting all of them, but here are some. So for example, we have conditionals. So if an abstract binding tree or APT satisfies phi, then we will execute E1. And the abstract binding tree will remain unchanged. And I also want to note that this notion here represents an abstract binding tree and the cursor context within it. And we also have, of course, if an APT does not satisfy phi, then we execute E2, and the APT remains unchanged. And then we have contexts. So given a prefix pi, if pi transforms an APT into a prime, then prefixing an editor expression with pi will result in E with the transformed APT. And then we have a substitution and cursor movement. So for insert operations, so given some operator and an encapsulated cursorless APT, which you can see by which is denoted by the hat here, then applying the insert operation will replace that APT with the given operator, where every argument has where we insert a hole for every argument for that operator, and this implies that the sort of the encapsulated APT is of sort S, which should be the same sort of the given operator O. And we have child operators, which, as the name implies, if we are encapsulating an operator with n children, we can then move to the ith child of that operator. And then we have the parent operator, which of course does the opposite. So if we are encapsulating a child of a node, then we can move up to the parent. And then we have conditionals. Here I will show a couple of them. So let's say that if an encapsulated APT does not satisfy phi, then the encapsulated APT does satisfy phi negated. And we have conjunctions such that if an encapsulated APT satisfies phi 1 and phi 2, then that means that the encapsulated APT satisfies the conjunction of phi 1 and phi 2. And then finally, we have a model logic. So if we are currently encapsulating some operator O, then we satisfy the at O operator. And we have this diamond, which tells us whether an operator exists in any subtree. So let's say that an encapsulated APT AI satisfies diamond O. Then also the parent of this APT, let's say that is encapsulated by the cursor, then diamond O is also satisfied. And of course, we have that if an encapsulated APT satisfies at O, then diamond O is also satisfied. So having the generalized editor calculus, we will now show how to encode it into a simplified lambda calculus with pairs and pattern matching and recursion. And assuming that the type system of the simplified lambda calculus is sound, and that the encoding is correct, then any instance of the editor will have the sound type system. And here are some of the terms and the types of the extended lambda calculus. So here we are able to represent the operators from our abstract syntax. And we also by types, we have function types, and we have the sorts from our abstract syntax, product types, and booleans. And the types of the operators can be deduced from the arity. So having the typing rules, we can then encode the ABTs the following way. And lastly, we also have encoding rules for all of the editor expressions. So having the editor calculus and the encoding, I will now talk about the implementation. So where some of the important choices concern how we represent the syntax, whether we want code generation or a generic model, and how we generate the source code, and how we implement the editor expressions. So in terms of early work or simply other work on abstract syntax specification, we have Metal, an early formalism presented in the 1980s. And we have the CFIR ASDL, which is also an early example, which stands for Abstract Syntax Definition Language. And we have Abstract Syntax Notation 1, which does have abstract syntax notation in its name, although it has primarily other use cases, such as transmitting data structures over the network. But all of these have a common problem, which is that they don't support binders. So for this reason, we decided to create our own specification language. And here I have a subset of an SQL dialect, where we have our sorts at the very top. So we have queries and commands and so on. And down here we have our operators, and we have their arity, and we have their terms, which would be used for, let's say, pretty printing, and we have the sorts. And also we want to be able to parse such a specification language. So we also created a more computer-friendly and parsable version of the specification language. Now, a question we stumble upon is if we should use a generic model or if we should generate code for an editor instance. So one of the upsides of having a generic model is that we don't need any code generation, which arguably is less work and less error prone. But this is less efficient, and it needs a lot of well-formedness checks written manually. However, on the other side, we have code generation where we can take advantage of algebraic data types, which can constrain us to only be able to create well-formed terms. However, this requires code generation, and it is hard to guarantee that the generated code always works. And we also notice that this question relates to the question of specialization in the work of partial evaluation. So we decided to go with the approach of generating source code. And for this, we used a package that was already built beforehand, which was very useful when integrated directly with the language specification parser. And here we have an example which looks a little bit like something that we wanted. So let's say that we have a sort statement, and we have which has and we have operators, assignment, statement from home, turn, and so on. Which takes argument. For example, assignment might take an ID and then expression. So we can sort of parse this information from our specification language, and then we can generate actual working Elm source code from that. I am running out of time, so I will jump over this quickly. Here we have we had a simple, not a simple, but we had an ambiguity in how we actually want to decompose AST. So we found a way to always decompose these AST as in exactly one way to get exactly one cursor context and one well-formed tree. And finally, we wanted to pick a good set of languages as examples, and we ended up with C, SQL, and text, since they are languages of different paradigms and purposes. And yeah, here I had some examples of how one can easily introduce syntax errors in C programs and in SQL queries and in text documents. And finally, here I have a screenshot of the of a working generated editor for the SQL language. And yeah, so in conclusion, we have presented a general editor calculus and shown how to encode it in a type lambda calculus, and we have an implementation. But some of the editor expressions are yet to be implemented. So we still need to handle context-sensitive syntax, and we need to implement views of the code being edited. So for future work, we want to finish the implementation, and we want to consider a more concise implementation, and this could maybe be in Haskell. And that was all from me.
Can you hear me?
Yes.
Excellent. All right, let's thank the speaker. I don't know if you can hear us, but
I can.
There was lots of applause there, even if you couldn't hear it.
I couldn't hear you.
Okay, yeah, we have plenty of time for questions. So does anyone have any questions? Okay. Well, I'm going to start off by asking you... you had a future work slide there. This seems like a nice basis for building these editors. How do you see this having practical impact? Is this going to influence the design of systems like Hazel, for instance?
Do you mean the creation of a syntax object structure editor like this, or do you mean going with a different implementation? I'm not sure if I'm
wondering, is this going to change the way in which people are actually building these kind of systems right now? Or is it just an academic exercise?
Well, I don't have a good answer for that. If some of the others, maybe Hans would like to chime in, I could imagine.
Oh, wow. Here I am. Hi, I'm Hans. I'm co-author of this, and I think if I were to say something, I would probably say that, I mean, this grew out of the same ambition as the synthesizer generator and the metal framework from INRIA back in the 1980s, namely to see if one can identify common principles for editors. So maybe one could imagine using this for a generator, but then one would need a lot of optimization to do this. But I think it's also got to do with the fact that, well, it would be nice if we could have a workbench for experimenting with programming languages in this setting of editing. Does that answer your question?
Can you still hear me? Yes, it does answer my question. We now have another question.
Thank you for the talk and the work. I don't live in CS, but anyway, I'm Annie Liu, and I happen to have used the synth generator for my PhD thesis. But since then, I haven't followed very closely with this editor, programming or creation. So are these new editors also generated from these syntax? I mean, from grammars or whatever types, or they just manually written based on some languages or their keywords? You mean not to, I assume, right, not to the based on the type size you did, but for all these practically used editors, right? People use a lot of them for JavaScript to just put a thing on the web. So how are they created now? Just manually programming each little thing?
Do you mean in terms of our implementation, or are you asking like for structure editors in general? I'm not sure if I'm following.
Just in general, right? Because how about the future? I mean, future, everybody using these editors written JavaScript on the web, right? That's the current. So, but are they writing in any principled way, or what I'm saying, just ad hoc programming?
Yeah, I am not sure of how it is going on in the real world with structure editors right now. I have not researched how that is going. If some of you other guys have anything to chime in with, that would be nice.
If I could say something here.
Oh, sure, go ahead.
I would say that a lot of the work that we've been doing here in this work is really got to do with the back end. Really, as you can see in Sune's presentation, the graphical interface, well, there isn't on at present. A couple of years ago, I supervised a bachelor's project here in Copenhagen that was mostly working on the front end. But I think the front end would have to be very specific for the concrete syntax that you're after. We're dealing with abstract syntax and whole backend machinery. I think one would have a different pretty printer for each of these settings, really.
Okay, all right, thank you. Yeah, this is a more abstract
question. We're going to have one more question. And yeah, before I forget, the coffee is upstairs after this.
But not for us.
Well, you have to find your own coffee, yeah.
Kenichi Asai from Ochanomizu University. I think this editor is for avoiding syntax errors. And I wonder if it can be also used for avoiding type errors.
I think that's a good question for one of you guys that worked on that part.
Yeah, I think the type system that we've got deals solely with making sure that the syntax tree is well formed. But my guess is that one could, I mean, if we think of attributes, we could annotate the AST with attributes and prevent type errors in that way, couldn't we? The attributes being types. I mean.
Hi, yeah, thanks for the talk. I have one question. So there's like been a recent interest, I guess, in editors for like collaborative editing. And there's a paper at Popple this year on Grow, which is like a Hüttel collaborative editing sort of framework. I'm wondering if you've thought about how to extend your calculus to distribute, like, or if that's kind of just like out of scope for now. It's a lot of work, so yeah.
Well, my take on that is that very early in the process, we designed this to only support one cursor. So yeah, that would be my answer. That no, we were not really looking into collaborative editing in this project.
No, I think one thing that might be making this a bit more complicated is that then we would have to redefine the translation, because one thing that's really nice about this work is that one can translate the editor calculus into some type lambda calculus, and that makes sure that everything's nice and sound.
Okay, thank you very much. We need to wrap up now because we're out of time, but thanks a lot for the talk and for your answers.